أشهد أن محمدًا رسول
Bismillahirrahmanirrahim. Thank you very much for inviting me. It's a really, really great pleasure to be here. I guess you want to know a little bit more about me.
Yes,
So essentially, I originally have been was trained as a medical doctor, studied at Cambridge, and whilst there, I did some of the modules from part 1B and 2 of the mathematical tripos. And eventually, over the years, carried on studying mathematics and some physics as well, finally culminating in a PhD in analytic number theory. But at the same time, has developed throughout that a very strong interest in theoretical physics, because some of the aspects of number theory that we currently understand are at the very heart of theoretical physics, which particularly there's a fashion for string theory and so forth, and many other things that the heart of which still lies number theory. So I then studied the masters in quantum field theory and fundamental forces, which is like essentially the pre-research qualification in particle physics. I did that at Imperial College. And as part of that, there was a very huge and large component of quantum theory. That's why the title of the course is Quantum Fields and Fundamental Forces. In fact, it's everything that you need to know about physics as we know it today to the boundary of physics. That's the type of study that I did. And so therefore, I had that opportunity during that time to be appointed for 2 years, in fact, as a research fellow under a Templeton Foundation, a Templeton Research Fellow at the Cambridge Muslim College. And whilst there, I then had studied further the ideas at the foundations of quantum theory, and then eventually developed a good relationship with Muslims in very many different establishments in different countries, and set up 2 sets of fairly large conferences in Cambridge Trinity Hall, and also furthered my research whilst at Imperial, trying to tie the 2 things together with published a paper in the Journal of Cognitive Sciences. So that will all tie together in a minute when you see what I'm talking about. The fundamental motivation behind what I do is the study of science as it is today in relation to our understanding of Islam as we understand it as revealed by Allah subhanahu wa ta'ala. We do not, my purpose was I'm always motivated by understanding the world, you see, not just understanding science in isolation, but how it relates to humanity. And it was a very, very big surprise to me during my early studies, that physics, at the heart of the physical universe, lies a very, very strong connection to humanity and mankind that pretty much will remain not very visible to you, because it's not really something the media ever projects, and you get much more airtime with evolutionists and Dawkins and things like this being pushed at you, but you won't actually hear much of the background that lies at the heart of quantum theory, as I'll explain to you in a minute. The reason I mentioned quantum theory is because that's where all some of the secrets have been revealed as to the nature of our physical world, and in particular, it's a story that goes back not just today, but around about 100 years. So we're talking about a story that has evolved, in fact, more than 100 years, but certainly 100 years. So it's remarkable that we can be sitting here today and still not know about it, especially as it relates immediately and directly to our personal lives, and most importantly, in relation to our faith as Muslims.
So inshallah, looking really forward to us getting into the details of that.
just to take one step back, so you qualified as a doctor at Cambridge, and then were you practicing your profession and pursuing studies on the side, or how did you juggle that?
Yes, I mean the beauty of what I chose as a career through medicine was that I chose to take a path which gave me more time. So initially general practice, and then eventually urgent care and out of hours work. Medically, it means that I could choose my time, and eventually I actually moved a lot of my working schedules around so that most of my working week was freed up to do research studies, and I was working more at weekends and evenings.
So was that PhD at Cambridge also?
No, the PhD was at Royal Holloway under Glyn Harmon, who's a professor of mathematics there, and then eventually after that the masters in theoretical physics is at Imperial College, and Cambridge has a very good name for many things. But one of the beauties of the unit, this research group at Imperial, is that they're very much connected to a very wide community, and that's slightly, I would say, very much at the forefront of the studies. In particular, it's founded by Abdus Salam, who in the 1960s, as you know, is a Muslim, Pakistani Muslim, who actually was one of the Nobel Prize winners at that time for unifying a couple of forces, along with Weinberg. And so there's a lot of a good reputation and a very strong, if you like, culture in understanding quantum foundations. It's the only place I know that offers a master's in quantum field theory and forces. Yeah.
Okay.
Yeah.
Okay. So you started to delve in trying to understand the quantum enigma, as you could say, trying to like get your head around it. And obviously, there's things that we're going to try to at least explore here from a very basic fundamental level. To first just to understand what are we saying when we speak about quantum mechanics. So I'm going to try to put on different hats, so I'm going to be asking you these questions. So I'll start from a basic layman's perspective. When we say quantum mechanics, what do we mean?
Right. Before I think I can answer this question, but you know, one of the most fundamental things that is misunderstood by the public is that it's just science, right? So just get it absolutely straight. It's special. It's special. It's got a name. It's become very well known. But that is the science of the world. So it is the science of the world as far as the physical structure of the universe can be taken. So, and the reason for the word quantum, I'll explain to you shortly, will comes from the fact that where we thought things were nice and, you know, continuous and smooth and had kind of endless values, energies could have values, any type, momentum could have values. All these things were discovered later on to be, to everybody's shock, that they weren't, that they were discrete packets. And I'll come on to that again. Perhaps I should give you a bit of background. If I could just give you some motivation, and sorry to take over and give you a bit of a talk, if I could just briefly give you the background.
Yeah.
So the motivation behind, I think, my view on quantum theory is basically trying to understand what is reality, what is real, and what are we. Yeah? So to start right from the alpha as a believer, as Muslims, we know that, and we believe and completely trust that we are nothing other than a creation of the most supreme creator, Allah subhanahu wa ta'ala. This is the alpha, and that we are not here as a random creation, a random purpose. So I know it's jumping back quite far, but this is the underlying motivation. Now, scientists previously, if I could just explain, were very open, even in the Western culture, including Isaac Newton and other scientists, Galileo, all these people, Kepler. Many of these early scientists were openly spoke of their faith and believed in God. So, and what's happened recently has been a strong change and bias in scientists, and it's moved away from being able to openly confess this, and scientists try to project this view that somehow that's not important. So if I go right back to the beginning, in a few steps, you'll see how we go from that, where I've just said, to where we are now, and then we can delve into quantum in more detail, so you understand the context. So if we're asking what is real, and what are you, who are you, what are you? I know as youngsters you're probably thinking, what am I asking you? But what I literally mean is, you actually, can you define what you are and who you are? And so I'll ask you something. So what is the scope of our perception as a human being? I can ask you very clearly that the range of a human being's vision is a tiny fraction of the entire electromagnetic spectrum. And what we hear is it's quite very limited. Dogs can hear a different range, bats hear different ranges, dolphins hear different ranges. We just hear it, and yet the actual range is vastly bigger than that. So what we're seeing and perceiving in science is just a tiny aspect of the real world. And even as we use machinery, they're still limited in how far we can go back in time, how far we can go with telescopes, how small we can go with microscope. We can't do it very well, and even with the most powerful physical tools we have in the universe, in this world today, do not be bluffed, right? We do not know the answers. We've got beautiful theories, but even with the particle accelerators, like the Large Hadron Collider, you can only reach a certain limit. So therefore, don't be fooled into believing that scientists know everything. Yeah, that's the first thing you must know. So when you go to school, if your teacher tells you that the world is made of atoms and chemicals, just remember that actually, although that's true at a certain level, it's not the full truth. There's far more to it that we don't really know, and you'll discover with time that that even atoms are not at all in any way fundamental. So that's so we're perceiving a tiny fraction of reality. So what I want to say to you is that there's something unusual about human beings. It's very strange. And absolutely nobody, not a scientist, not a Muslim or a Christian or not a philosopher, can explain it, and we do not have an answer. And that strange thing is that we have the two major gifts. Number one is we can comprehend and think and understand, and we can be aware of things. I'm not sure how much, like for instance, an earthworm is actually aware. It certainly doesn't have the same visual perceptions and auditory, and there are different levels of perception and awareness. But human beings are aware. You're aware that it's slightly warm. You're sitting in this room, the fans are on, and it's the sun's coming through the windows. You're aware of where we are, but not every being is aware. Secondly, we're able to make sense of the world in a way that certainly I don't think, for instance, a cat or a dog could make sense of the world in a far greater way. So the magical bit is this. In 1960, Wigner, who was a brilliant physicist, wrote a paper a very famous paper called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Now, I'm just using the word mathematics. Don't believe also that mathematics explains everything. There's an illusion. Just take this illusion away. I have a PhD in mathematics. I can tell you it doesn't explain everything. But there's something unusual about the tool. Mathematics has the ability to penetrate as a language into the deepest part of the physical world, far beyond what we would expect. It's too effective. It's way too effective. And what is mathematics? Well, mathematics is just a way of human beings working out what are patterns in this world, how things relate to each other. So don't get it wrong. Mathematics is not science. Yes? Remember this. It's used for science. Mathematics maybe is a sort of science in itself, but it's not science. It's the study of patterns, the relationships between those patterns. Yeah, we talk of numbers. Numbers are a type of pattern and forms. They also study of shapes, and structures. So that's mathematics, like symmetries, and understanding bigger numbers are infinities and infinities. That's mathematics. And the difference between mathematics and science is that mathematics has its own proofs or theorems. Theorems are true. They're absolutely true. They can't be disproved because they're proved rationally. So whereas the difference is science isn't like that. Now here's some fundamental fact about science. A theory is not a truth. Now, that's a strange thing for me to say, but it's not a truth. Yeah? A theory is the best model we have at the moment of what we think is the truth. That's a theory. Yeah? Now, that's happened over time, many times, and the most fundamental time we'll see was quantum theory. But another example, a very good example, is what happened to the nature of time and space. And about just over 120 years ago, we discovered that actually time was not a fixed object. It varies. It depends on your movement. It depends on where you are close to gravitational field. And there are a multitude of things that we believed were absolute truths about, and our theories are perfect. And that's really where we're coming into quantum theory now. There's a belief, the classical view of the world, we could explain everything, was absolutely final. And so the truth is, science has theories, but theories are just the best model we have at the moment, accurate models of how the world works, but they're not the truth as in we believe with our eyes shut this is the complete final answer, right? So it does not, that's the difference between science and mathematics. So just before I go to quantum theory, the reason things have gone a bit blurred and this currently is because we have this continuously evolving theories and ideas, we now have this problem that scientists are tending to project their opinion on theories. So we now reach the point where physics is no longer, and science generally, is now actually plagued with opinions and rather than experimental proofs. So you've all heard of string theory, yeah?
Yep.
And you've all heard of extra dimensions and things. Yeah.
Multiverse.
Has anyone ever seen a string? Has anyone ever seen an extra dimension? Yeah. Has anyone seen another verse of the multiverses? And the answer is no. Does anyone even have any idea if what they're saying is actually true? And the answer is no. And okay, there's some suspicion that things might be like that, but they're not. They're just theories which are not tested. So yet despite that, they have the hold the name theory, and the word theory is being abused here because it should be experimentally proved. But what I'm going to talk to you about is theory that has experimental proof. So let's stick with what. So the most important thing is let's stick to what we actually know, rather than the wool that's going to be pulled over your eyes by millions of scientists and theologians throughout the world. So just be careful that somebody who comes across as a physicist with massive authority probably doesn't have the answers that you think they do. Yeah. So just be careful. So I'm going to go into quantum theory in a minute. Well, I'll just start it off and then you can start asking questions.
Yeah.
So what I would say to you is that the most important thing about quantum theory is that it should really be an example of how science has finally embarrassed itself and shot itself in its foot. And you'll see that quantum theory is the best example of that. And what has happened is that the reason it shot itself in its foot, it's become embarrassed and shied away, is because the theory says man is somewhat important and that we're not randomly crawling off a rock evolved like Richard Dawkins would like have you believe. Some random processes. It's something far greater than that. You will understand in a minute what I mean about that. So mankind, or something to do with mankind's attributes, which I referred to at the beginning, which is its ability to think, to comprehend the world, becomes not just an interesting thing, but becomes the very reason where the physical theory exists, ironically, and how perhaps even reality is the way it is. So that's what's happened. So last couple of comments. Hope you don't mind me carrying on. Is that okay?
Yes,
Yeah. Just a couple of more things that I just want to point out is the other problem with science is that there's a drive towards reductionism, by which I mean there's a belief that somehow the more basic you can get down to the fundamental units, that somehow you can build up the entire world from those little tiny building blocks. So billions are spent on particle accelerators. So we got down to about 25 different particles, and there's endless search by physicists, theoretical physicists, who hanging their head low, and in massive disappointment, I tell you right now, they cannot find all the particles that they hope to see from some of the theories, particularly like supersymmetries predict a whole series of particles. Nobody spotted them, and for like many decades, the biggest result we had was the Higgs boson. But apart from that, there's no real progress for many decades in theoretical physics on an experimental level. Right? We've found nothing incredibly new. Yet, there's a belief that the very fundamental small objects can build into a picture of reality. So somehow we could build in everything we know about the known universe from that. But I can tell you that's not true. There's no way that any physicist could ever explain to you why something's beautiful, or why you fell in love, or why something tastes good to you or didn't taste good to you, or whether something smells nice, or how you feel. Nobody knows the answers to these. And you cannot build a picture of reality from fundamental physics to that level. I mean, try it. It's not possible. Not because the theory's rubbish, because it's not a very good theory. It's a very, very highly developed theory, but it simply doesn't reach that point. It doesn't ask those questions. We're talking at a different level. And so therefore, the other thing I'll just say to you is that, so they're reducing things to the tiniest point that cannot automatically allow you, with all the equations in the world, to build up to the picture of the universe, right? So there isn't a theory of everything, right? Just to eradicate that. There is no theory of everything. Yeah? Right. The other thing I should add to you is that we know, and again I won't go into any further detail, just very briefly, that the higher order structures containing objects of many more than one or two things, fundamental things, have properties that you can't predict from the reduced state. That's as much as I'll say. I mean, we'll give you examples of that later on. But we now can at this point begin quantum theory to give you the story. So that's just the background. So okay. So do you want me to just give you a little brief intro, then you can ask questions? So the big intro to quantum theory is this: that in a nutshell, up to just before 100 years ago, physics was and science generally was a beautifully thought to be fully understood theory. Everything was perfectly determined. So, unlike what we know now, it was believed that we could just write down an equation. I could work out the orbits of the planets to perfection. We knew everything about particles, and waves were waves, and particles were particles, and they all interacted in the way that we knew light was an electromagnetic wave, and all tiny little particles behaved like little tiny billiard balls, and everything was perfect. We could write the equation down. That was the picture. Then it was at the beginning of the last century that physicists started to run into problems. And the most important physicist, one of the most key figures who won the Nobel Prize for it, was not for relativity, was actually Einstein for the photoelectric effect. And another couple of very important results came about that made us realize that, in fact, particles were not really particles, and they were not really waves either, a bit of something in between. And waves are not really waves, and there's something like particles, but they're not really either of those two things either. And this whole physical theory, quantum theory, basically describes all matter and all, in fact, all forces, but sticking with matter and waves as being compartmentalized into small particles and waves. So there's some wave behavior in particles, and there's some particle behavior in waves, and in fact the truth is they're neither one or the other, they're somewhere in between.
So I just want to take this from a layman's perspective, and this is where people can start asking questions, and we can start to delve in this field a bit more. So what you're saying is, up until 100 years ago, physicists were, I guess they were following the physics of the Isaac Newton and whatnot, and things were very very, very clear for them as such. And then obviously when they've gotten down to the quantum level, things, as you said, were now starting to kind of like pull the rug beneath their feet as such. So what were some of those areas where at the quantum level that started to do that, and what was it that they were beginning to learn at the quantum level that was now contradicting what they understood from Newtonian physics?
Yeah, so keeping things really simple. It sounds like it's fairly heavy science, but if you're patient with what I'm going to say, you'll understand that the significance. The first thing is we always believe that somehow waves like light were just waves, and it was a series of different experiments, particularly the photoelectric effect. I point to that one as a first example. Well, Einstein had noticed that when you shine light at different frequencies to a surface of a metal, it released electrons, which are like the small particles of. But the energy of the electrons depended on the frequency. But if you look at them, no matter how much you turn the actual brightness up, it never changed anything. And you realise that the reason was that in each the wave, the light beam was actually made up of multiple tiny, if you like, particles of light, which were imparting just a certain amount of energy to the surface electron. So that was the first sign that something was not right. That it was that we got it wrong about light, and then I'll go straight on to the idea that the atom was first of all understood and thought that there was electrons orbiting the centre of, like you're taught at school, you got protons and neutrons in the centre, and you've got these electrons spinning around. And then we ran into problems, because if you look at that picture and work it out, there was a physicist called Niels Bohr realised that if you did have this is really actually true, that the electrons would spiral in and it would collapse. There's no way that you can have this sort of arrangement. Naturally, the electrons spiraling. But more importantly, if you heat up certain substances like salt, or sodium, or potassium, or certain gases, they release a certain amount of light. If you analyse the light is not in one type of colour or frequency, but it's in multiple discrete colours, a bit like those bands. There's strict bands of colours. It doesn't have every frequency, and that can never be explained by an electron spinning around freely around the orbit. Because what happens when you heat something up, it should actually excite the electrons, and they move and accelerate, they release light. So what actually was found was that the only way to explain this was that somehow electrons could jump from one distance from the neutron, if you like, or the nucleus, in discrete jumps, without anything in between. They could simply just go from one point to another point without anything in between. Now that sounds bizarre, and there was no physical theory to explain that, because we didn't understand any of these things at that time. But Niels Bohr was the genius behind the idea that something was wrong with this model. So the next thing I will explain to you probably gives you the biggest mystery of all, and that really, I would say to you, if you want to know quantum theory, just know this experiment, and you really know the one thing that makes quantum theory what it is, and what Richard Feynman, a famous physicist, really brilliant physicist in quantum mechanics and quantum theory, said it's probably the most biggest mystery of the whole of quantum theory. It's demonstrated in this simple looking experiment. So just to get a grip on this, it will pretty much sum up everything, yet it's such a simple looking experiment. It's a double slit experiment. So I'm just going to give you an idea that here's two barriers. These are the barriers here, 1 and 2. Forget about this bit here. Now, you could think of them as a wall and another wall, and these could be like balls or footballs or small pebbles. And in the first barrier, the first wall, there's 2 gaps. Now, if you were to kick like footballs through those gaps, you know that probably they'll manage, as long as they're wide, the gap's wide enough, the balls will either go through the gap and hit the second barrier, which is the second one there on the right. So you can't actually see my arrow pointing. I just point to the first and second barrier. So you know, this is the first barrier, that's the second one. That's the gaps. And the ball will go through and hit this wall here. Okay? This is just the same wall sort of swiveled round, so you can see where they've hit. Okay? So there's no extra wall. That's just a picture of that wall face on, so you can see where the balls have arranged. See? So if you look at that, this is what you'd expect to happen with a ball or a particle or a stone or a pebble, or for that matter an electron or an atom. You just throw things through a gap and it comes through and hits a little pile on one side, another pile on the other side. But when you actually do this, when you compare that, what would happen with waves don't do that. Waves do something different. Here's somebody throwing pebbles into water, and you can see the ripples going out. And then you see that where the ripples cross over, they interfere.
That's your question here.
Yeah, sure.
So, from a very basic level, why was it even important for scientists or physicists to try to determine if something is behaving as a particle or as a wave? Why was it?
No, actually, the reason for it was to try to understand the structure of the atom. All of this is down to trying to understand, and the experiments were there just to elucidate that. They weren't trying to find out if there were particles or waves. This is by chance, or by experimental chance, they found that this was happening, because the reason for it is you'll see in a minute that particles can actually go through little gaps like that and spread out as if they're a wave and behave and disperse like a wave. You'll see, and that's what will happen. And the reason, and in this is the heart of everything. So if you want to know quantum theory, just as I said, just keep focusing on what I'm going to say, because then you'll get a grip on it very, very quickly. So it wasn't that they were looking for, to answer your question, they weren't looking for particles wave differences. They were just doing experiments, and these as observations that were found by experimental observation, by chance. And you see that when they were looking for things like like Compton, and looking at the structure of atoms, firing large particles through, trying to understand what an atom was made of. So here, this is what happens with waves. They interfere. And is a little picture of waves upside on, wobbling together, and they can join together and they can interfere and cancel out. So the left side, you can see the joining together, constructed interfering, the one on the right side cancelling out. So when you send particles through, waves through two slits, you get a wavefront going through, and then you get two sets of similar to the pebbles, ripples coming out, interfering. When they actually, and this, you can do it too. You don't need a science degree. You just go to any pond, or just be careful with a bathtub and fill it up, or sink. Just put two little, see what happens. You get ripples coming out like this, and they cross over. If you look at when they reach the other side, those beams, those light beams, they're not really light beams. They're just representations of where the waves have constructively interfered and become a big peak. And the black areas are where they've destroyed, destructively interfered. So this is what happens. If you could see it coming on, you'll see peak areas, and you'll see areas which are flattened out. And you'll see troughs as well. But you'll see where there are peaks and troughs, you'll see the representation of beams, and the other side you'll see it. So this is what waves do. Have you understood what I'm saying?
Yeah.
It's not difficult. I hope it's very simple. You can't see that very well, but it's just another perspective on the same problem. So this is what actually what happens when you sort of fire a beam of particles. Now, let me be even more specific. You don't need a beam of particles. You just need. Let's take an electron. If you basically understand an electron is, what an electron is. Just this tiny electrical charge, negative charge that goes around the center, around the atom. Yeah.
They typically, when they're explaining this, they usually say this. They shoot a particle through, and sometimes they use an electron. How, how have they tried this in greater
Yeah.
like in terms of atoms themselves,
Yes.
they also behave like
Yes,
this?
yes,
Whole atoms behave
yes,
like
that's
this?
right. Yeah, and this, what you're asking is a very important question because things behave like it up to a certain point.
Right.
Yeah. So if you throw a football through it, you obviously won't see it. But if you see a large atoms, you still see it.
And do those atoms also? I think you're going to allude
large
to this.
molecule.
You're going to allude to this after, in terms of when you're shooting them one at a time and they behave still as a wave, for example.
Yeah.
Do the atoms also behave with that?
Exactly the same.
Exactly the same.
Exactly the same. Yeah, even large molecules, anything that's up to a certain point. I'll come to that. A very, very important question you're asking in a minute. But first of all, we still haven't got to the point here. The crucial point is we haven't reached that yet, which is is that if you look at any atom or particle or molecule, whatever, let's stick with the simple example of a tiny ball like an electron. You can imagine it as a tiny ball for now. It should behave like that. So you see on the left-hand side, they go through a slit and then you write it in two piles, just like we did with footballs. But when you actually do it, and you don't do them as a big beam, you can just do them one electron at a time, you build up a pattern on the other side, and it looks, instead of looking like arriving at 2 points, it looked just like the wave pattern, like a spectrum, like you see. I can't see it very well. Can you see that?
Yeah.
Now on the left-hand side, a few, 1 or 2, 3, and the more and more you do, you have to do millions, and you find that, or many trillions, you'll see that this pattern emerges, rather than like a ball being thrown through to a slot, 2 slits, and arriving at 2 points. It presents itself like that, just like a wave does. So what's happened is that this actual particle is actually behaving, just call it in this particular example, an electron is behaving exactly like a wave. Now, now here comes, switch on your tuning devices and listen carefully, because this is it. This is the mystery the biggest mystery in the entire universe, and at the heart of everything. It seems like a simple experiment, but the entire field of quantum theory is built up from this. Right? This is it. So once you've understood the dilemma here, you'll understand what's happened. The dilemma here is this. As soon as you put some sort of recording device on the slot to see, firing one electron at a time, to see which slit it goes through, I said slot, I mean slit, you see what happens. You're aware of it, you measure it, you say, blip, it's gone to the right-hand side, blip, no, the left-hand side, blip, left, blip, right, and then you keep measuring it and recording every time it goes through, and you know which one it goes through. The entire behaviour of the electron, and remember this is important, that recording device is not interfering with it at all. It's not interfering with the electron. It's not stopping its movement. It's not a magnetic field. Or, it's not deflecting it in any way. It's completely, it's not obstructing its movement in any way at all. It's not interfering with it. You're just recording. You're just recording which slot it goes through, and it's very easy to do without any interference at all. What happens is that because you know which one it's going through, and that's the only difference, and because you recorded it, the wave behaviour suddenly changes, and it becomes like a ball again. So the electron now, is behaving like a ball, and the only difference is that you've actually been aware of it. It's like a magic trick. It shouldn't happen, and if you take it away and stop being aware of it, you don't know which one it goes through, it becomes like that again, a wave again. And this is a mystery.
So essentially what you're saying is, when you put your detector on it, it changes its behavior.
Yeah, when you're aware of it,
when you're aware of it.
Measure it.
But when you're leaving it, you take the detectors away.
Yep.
It starts to behave like a wave again.
Exactly, and that's exactly it. And the thing is, what I would say a bit more to make it a bit more clear is those spectrum thing you see at the top, where there are many waves. You can think of those as all possible places, and there are many of them going on, that a single electron could end up, right? That's what it says. It could end up here, could end up there, could end up there. Where it's black, it means it can't end up there. Yeah? That's what it means. But one electron you fire it through, you know it's going to end up with one of those places, but nowhere else. But when you look at the bottom one, the places where it can end up is just two. It directly in line with the first slit, or directly in line with the second.
So just to make it clear, the enigma is, the problem is, the thing that doesn't make sense is why does it just change all of a sudden?
Yeah.
Right?
The problem is that if you all play football after this, or play golf or anything, try it out and see what happens. You cannot get that behaviour from a particle. The particles do not behave like that at our scale. But down at the quantum level, at the tiny level, at a certain level, which is what you're referring to, it doesn't do that. In fact, worse than that, you cannot know where the ball will end up. You can't know until you actually observe it. This is the point. You don't know where it's going to go. In that particular example, if you were playing a blindfold, you're kicking a ball through, you should be literally kicking a ball through these slots with a blindfold on, and it can end up in like maybe 1,000 places, but only of those. As soon as you take the blindfold off, it can only end up in 2 places. But you know that every time you kick the ball through many times with your blindfold on, it's ended up with places where you can't possibly have sent it.
Have there been experiments where they've had 3 slits?
Yeah, it's the same thing, but it doesn't actually make an awful lot of difference because you basically just going to have more interference. That's all. So it won't make. The minimum is 2.
They call this the collapse of the waveform.
Yeah, absolutely. And we'll come on to that because the next thing is how do you make sense of this? First of all, we can't talk of wave functions because we don't even know what this is before we talk about wave functions.
Right.
So if you were given the challenge to try and explain this, how would you do it? Now forget about atoms. Think about balls. Yeah, go ahead.
Does it make a difference if we shoot them one by one or if we shoot them all at once?
Absolutely not. And these patterns are built up usually by one. You can do that. And ironically, you will see that in fact it forms as yes, gradually. If you do it one by one, you get dot 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 dot. Yeah, exactly. At one state, you just get a dispersion. So you would get something going on. It's like with light can disperse. So you get the edge dispersion, but you don't get the interference. So you won't get the same the phenomenon. And also the other problem is that it's not going to be so dramatic an effect because there's only one slit it can go through.
No,
the problem.
If it's been
Yeah.
monitored
Yeah.
to see where it's going to go
Yeah.
after it's gone through the slit, does it change its behavior?
Yes, it will change its behaviour, exactly.
Even
But
though
this
the
is more
slit-
absolutely, and this is a more dramatic effect because you can see it because of interference involved as well. But yeah, it's exactly the same because electrons will disperse just like a wave through a single slit. But we always talk of a double slit because here you have the option of actually calculating, working out which one it goes through. You see a dramatic change in the result, in the visual appearance.
Can I just ask that? Is it logically then to assume that if this is happening at the atomic scale, then by inference, if you scale it up, this is also then just the multiplication of what's happening just at the.
Absolutely. So what you're saying is that, what you again, I'll come on to that again. The reason I say that is because it won't make logical sense to just say it now. But in the word, when you look at larger objects, usually, like you're talking about a very large collection of objects, a whole load of other things happen, whereby there's something called environmental decoherence, and also the classical level that we know emerges, and you can't detect this. And the reason for that is because it was best studied by de Broglie, who tried to say, well, if an atom is like that, is behaving like a wave, the most basic example is what is the wavelength of the atom, right? So he came up with a very, very simple relationship that the wavelength is just a constant inversely proportional to the momentum. So it's just 1 over the momentum. So it's actually Planck constant. It's a very important constant over the momentum. So it can have a momentum. So a very, very large object like you is such a huge momentum that your wavelength is just almost 0. So you can try running through slots, but you're not going to do this because it's too big, and it's not detectable. That's a very, very crude example of what I'm trying to say. So in other words, the effect is not noticeable after a certain. But the other point, it's still there.
Yeah.
You still have a wavelength.
But
Yeah.
Just because we can't detect it, does that mean that we just don't have the ability to detect it, or does it disappear completely?
No, it doesn't disappear. It is there. You still have the wavelength, which the wavelengths again. This is very, very important.
Sorry,
Yeah.
is there a point where does that object become observable? Like when you can see something, is that when we are no longer able to detect this wave?
No, again, you're asking indirectly the same question that Abu Bakr is asking, which is the scale, which I'll come on to in a minute. But it just suffice it to say, for very simple purposes, just for now, the bigger the object, the tinier the wavelengths, and you're not going to be able to run through, charge a large ball through 2 slots and see interference pattern, but you're going to see a tiny level you do, and there's a certain point at which it crosses over from classical to cross quantum behavior. So, but I'll come on to this again.
And these experiments,
Yeah.
I read recently that it's kind of pretty much now established. No matter how they do them,
Yeah.
the results are the same.
Yeah,
so
absolutely.
It's been tested again and again and again, and consistently we're getting the same results.
Absolutely, this is beyond dispute. It's not even a theory. It's not a theory. It's just an observation.
No.
There's no. By the way, just to me, this is not an This is not a theory. This just happens. Just like you go shopping and it costs you that much to buy something at shops, or you trip over a stone, it hurts. It's just fact. You just observe it. There's no theory. The theory comes now. The theory will follow. The quantum theory comes from this,
Right.
which I'll explain now. So in other words, it's an experiment. It's a controlled experiment. You can repeat it endlessly, and you will get the same result. So okay, I've jumped a little bit straight into the quantum theory, right? So let me explain this slide to you, so you will understand what I'm trying to say. It took Erwin Schrodinger, and actually separately, Heisenberg, 2 different physicists, to come up with some way of modelling some sort of physical theory that could explain this behaviour. And in a nutshell, it's based upon the idea that because you don't know which way this electron will go, left or right, you just have some sort of probability of it going left or right. So that's all you have. So we have this wonderful object called psi, which everyone talks about as the wave function, and it's the most fundamental object we know, actually, in a way, in terms of physics, because you can only know so much about a system. So this particular thing is the closest to what you call the wave associated with an object. So what is this wave? Well, de Broglie was talking about a real wavelength, like a literal wave that you could be. But this is actually not the same type of wave. This gives you the probability, and it is the wave associated with the object, but it's a probability. So here, without looking at it in too much of a scary way, it is an object which I'll explain in a moment, associates a probability of finding something somewhere. So in this case, this wave function test tells you that this psi is just a sort of like a function you don't learn at school, like a quadratic curve. It tells you when it's high, that's the most likely probability of finding something there. And if it's really low or 0, it says probability 0. That's all it says. So in this case, it would be an example. This tells you, if I ignore time for the moment, it just tells you where an electron will be. So if you imagine this wall is like a long x-axis, and there's the wobbly function, across the whole wall. The areas where the wave function is high is the area where you're most likely to find an electron. And in certain instances, where you can confine an electron to a certain place, this wave is a bit more predictable and a bit more simple to look at. And this equation, which is the Schrodinger equation, is really very simple to look at, even though it looks complicated. It just says there's a sort of term on the left-hand side, which is like the kinetic energy of this wave. And then the next bit is the potential energy of a wave, just like we heard at school, the kinetic and potential energy of a ball. And there's a term on the right that deals with the time. So the beautiful thing about this so-called wave thing, before I explain what it is it looks like a typical classical equation. It's got a nice, smooth, you can solve it, yeah? You can work it out just like, the position and the momentum of a ball. But in this case, you're looking at the position and momentum and the evolution of this wave function. So what is this wave function? Well, in fact, it's the only, if you, to square it, you find the amplitude of it, if you basically find the squared modulus of this wave function, it gives the exact probabilities of where the ball will be, in this case electron will be. So if you were to find the wave function of this electron here, the wave function essentially is saying that where those big strips are, the wave function is saying that's where the electron is going to be. It's 80% of the time there, it could be possibly 20% chance it might be there, or, something like that. We could say that 90% chance of it being there, 1% chance of it being there, 0.5% chance of it being there. It basically gives you a range of probabilities, and there's the problem. The wave function gives you the top bit. It gives you a picture of where all the possible values of this position could be. And the same, you will see that quantum theory says the same about its energy, its momentum. It gives you a whole range of possible values. That's all it does. That's all it does. So when you look at the wave function, you extract from it this via this equation all the possible values of where it could be. And that's the best we can do. That's as far as physics goes. You can't know where it will be until you measure it. And the mystery is, when you measure it, it will collapse into one of the possible values. Yeah? So that's the mystery. And you only have probabilities. It doesn't tell you how to measure. And there comes the whole mystery of quantum theory, which you'll see unfolding now, that forget about everything that scientists tell you. So forget about the mysteries that you hear, and don't be frightened of the equation. It just says that I don't know where anything really is. It could be any of those places. The equation tells you, it gives you a very, very, very precise probability, and it works of where it will be. If you know something's 99% probability that it's going to be here, it's going to be 99%, and you can repeat the experiment many, many, many times, and these results are statistical. You send the particle through the same, whatever it is, circumstances 1 billion times, and you'll find that it really gives you 99% probability. And that's the beauty of the wave function. It's very, very accurate, and your mobile phones depend on this, just like our computers and everything, the technology.
Explain that, because we hear that quite a lot. Yeah. What does that mean? That how is it that our phones are also? Yeah. How do
well, because you look at basic electronic circuits, you can't use basic the sort of physics that you use for footballs. You have to use this, and without this, it doesn't work. You can't work it out. You have to use these calculations to do it. And there are effects that occur, like you will see things you may have bandied around, things like quantum tunneling and things like that, which actually do occur. They affect your components like capacitors, resistors, circuits, and everything. All depends on the physics that you have to use this equation or similar equations to work out what's happening. You can't use the normal equations. So you need this to work it out. You need computers to work it out for you. Yeah. So this is the only language you have. This is the only language that works.
Is that because the equation works at that level? Yeah. Or is it because it's working at the quantum level? Is it because that equation is working at that level?
Because the equation is the only description of reality at that level. There's no. You've got to throw away your normal pictures of reality. There is no other reality. There is just this these set of probabilities, and then when you measure something, you know it's going to fall into one of those possibilities. That's all you have, And then when you do the calculations, it's very, very accurate, and it gives you very precise measurements for that can be actually used at a practical level, because even though these statistical results, they're very, very reliable statistical results. So it's not because we're using some sort of fake construct. That's the whole point of this discussion, which you'll see in a minute, which will come out in a minute. So this is the wave function. So we're moving on from that. So this is the picture of reality. So have we got anything useful? And so much so that I'll tell you right now, Schrodinger got so cheesed off. Einstein says this is rubbish. And Schrodinger got so cheesed off, he spent all his time doing studies in biology and doing a whole series of lectures in Dublin on what is life. And a lot of physicists lost faith. Einstein disbanded it, said it cannot be true because this is just random probability. How can life be determined by that? And why does a man or a human being or someone have to come along to measure it to know where something really is? In fact, more than that, your Measurement Act has placed it there.
Well,
yeah. This is the fundamental problem. Your act of taking this fuzzy object has placed something there. Before that, it didn't even exist. But this is the point I'm going to come to. And this is the crux of it all. I'll be real. Let me give you the final chapter before the first chapter. Reality is dependent on our human consciousness. The world does not exist without us. It's the other way around.
It's a mental universe.
Yeah, absolutely. Absolutely.
This goes back to that thing: if a tree falls into place, will anyone hit it? If
That's
it's not there,
exactly.
well,
And that will come into a beautiful picture I'll explain to you in a minute. So can I collapse the whole of quantum theory down to this experiment, that we don't know where anything is, we just know where the range of possibilities. And we've got a very clever equation that tells us all the possible places. That's clever, right? But we don't know what happens when we measure it. And the reality is, and here, let me put it into more perspective than that. I can show you this picture. Okay, it's not a great picture, but it gives you an idea. These are the possible places where in this room maybe an electron might be, until you go and measure it, right? And then it will suddenly appear at one point. And it's your active human awareness and measurement that has created its position and its momentum in space. And there's
So I think I was trying to ask this question earlier, that you have a range of possibilities or probabilities, and then your act, obviously in this specific experiment of a double slit, forces or somehow affects those different possible ranges into those two.
Yes, or one of those. You'll find that actually the equation is very beautiful, because it actually gives you all possible outcomes, not the actual outcome. And when you measure it, it will be one of those possible outcomes.
So the thing is, what I guess the crux of it, which we're trying to allude to, is that. And we're going to talk about this much more about consciousness and that.
Yes, we're coming to that.
And how the mental state, how that's affecting the physical world.
Yeah.
The mental state affecting the physical world. Just generally though, and we don't have to go to the specifics, but have there been other experiments done, not using the double slit, that also affect the physical reality? So that the ranges of probabilities become more specific with what we're trying to do. Because obviously the act of, for us,
shows awareness. Any of the experiments shows
every single experiment has at the quantum level, for all parameters, dynamical parameters behave like this.
Really?
Everything.
What other examples do you have?
Oh, you look at position, momentum. You've got. For instance, energy, and even you will see right down to the very, very core level, every single dynamical variable. There aren't that many dynamical variables anyway. For a particle, you know position and momentum, you know energy levels, and that's pretty much gives you everything you need to know about an object. But this happens at every single level, to the point where you can talk about other things which I haven't mentioned. I suppose I should say them, like things like particle spin, at which you can measure polarization of light, for instance. You know, light has a polarization. Everything behaves this way. Every single
So if
thing.
you don't measure the light, it doesn't
Doesn't have a polarization. Doesn't have a fixed polarization. No, you have to measure it. And before that, it doesn't have any fixed polarization.
It doesn't.
You actually have to observe and measure the polarization. And when you do the slit, you have polaroid lenses. That forces it into one line. So effectively, you've measured it. But before that, it's not actually got a fixed polarization.
How do we know it doesn't have?
You ask, that is going to be the big chapter.
Okay, right.
Yeah, because you haven't reached that point yet. So I'm just giving you the basic idea. So to kind of drum it into your minds, we have a picture of a theory, magnificent theory, that tells you all possibilities, but not which one. And we're still dependent on human beings doing an observation to decide which one and create which one. And that is the truth. Okay, just a quick word on this equation. I just wanted to point out something called the third postulate. If somebody throws, their muscles around at you, say they know a lot about quantum theory, just ask them about Postulate 3, right? The third postulate. Okay, tell us about observables associated with some sort of mathematical thing called an operator. Okay, and it gives you a range of possibilities. But there is absolutely no mechanism by which the measurement actually comes about. There's none. It just says it's going to be one of those. That's the third postulate. There's no answer to that. And the reason for that is that active measurement is mathematically stochastic, meaning that it's probabilistic. And when it comes out, it's like throwing a dice, right? So it's going to be one of those 6 heads. The equation of motion, which is what we call Schrodinger's equation, is a smooth equation which you just calculate like when you throw a ball in the air, and you can see where where its position is, and a nice classical picture of throwing a ball in a projectile or something like that. That's a nice smooth equation. But what you're finding when you find that smooth result is just the wave function. The wave function doesn't give you any more information apart from those range of points. You have to go and measure it, and that's an abrupt event. And there's no mathematical result. Okay? Throw your muscles at the physicists, and those who are atheists who say that they will understand that everything is understood. Well, the most basic thing is not understood, and this is the most basic thing in the whole of physical science. And I can tell you that right now. It's factually true. We call it the measurement problem, and people might call it the measurement paradox, but careful. A paradox is something that has an explanation, okay? But you just didn't quite understand it properly. It's not a paradox, it's a problem, right? Because it's a problem for science. So one more thing. I want to say one more thing about quantum states, which is different from the real world.
Just ask one
Yeah.
question. Fill us in after this. With this. But how does Islam explain this in your mind?
That is a question that can come later.
Yes.
Yeah, it's too big a question. We'll come on to that in a minute. So we got to the third postulate, which I just wanted to point out, is the only explanation we have for measurements. And there isn't a measurement explanation, sorry, retract that. So it shows only how possible measurements can result in certain outcomes, but it doesn't give you any mechanism for actual measurement. Okay, so I want to now just briefly mention something really very, very important. That's just, again, you see this on the front of book covers, and people talk about it all the time, but I don't know if anybody really explains it very well. So, having understood that the wave function is just essentially a clever range of possibilities, of which we will obtain one when measuring. The other big thing about quantum theory is what's broadly known as superposition. So this usually you'll see it on the front of books and inside books with Schrodinger's cat, right? Is a classic example of how that's demonstrated or explained. So why is this important, and what does it actually mean? Well, to go back to the original double slit experiment, if you think about it, we don't really know until we actually measure whether one electron that we send through that double slit is going to go through the first slit or the second slit. Right? We don't know until you measure it. So, and yet when it's in that state, it's behaving like a wave. So Schrodinger coined this particular example as an analogy. It's like a thought experiment, in a way to try to ridicule it, but because he wasn't happy with the idea, but he gave this example. He said, if you take a cat, right, and put it inside a box, and there's some poison inside the box, but you cannot know until you open the box what's going to happen to the cat. Okay? So the question is it dead or alive by the time you open the box? Has it broken the seal and taken the poison, or is it just having a snooze and it's still alive? Yeah. You could set it up theoretically in your mind that there's a 50-50 chance either thing could happen. Suppose, it doesn't have to be. So if I was to ask you, if there was no other way of measuring it, how would you know if the cat was dead or alive? Any answers? Any suggestions? Yeah, exactly. There's no other way. So we don't know until. But before that time, there's something. This is a good analogy, by the way, even though it seems so absurd. But it's a very, very good analogy. It explains the quantum effect. Maybe not the cat, for real cats as such, but who knows? Because I know for physicists that the quantum theory can be extrapolated and used at different scales. But we're not going to talk about that now. But the point is, you don't know whether the cat's dead or alive until you open the box to check. Now, that is a big dilemma, because here we go. Here's an example. Here's how you sort of write it down. You just say there's a little cat alive state. We call it a state situation where it's alive. That's actually represented by like a sort of a wave function, in fact. And there's the other state where a cat's dead, and you've got equal possibility of either happening. That going back to the slit that you saw here, we don't know which slit it's gone through. You just know it could be one or the other, and you have a rough idea of the ratio of probabilities, that's all. So what we say is that before the measurement, the cat is both dead and alive. Now that's a really absurd situation, but this is what Schrodinger was trying to ridicule by saying that before that, it's not either dead nor alive, but it's in a state of both being dead and alive, both. And
he was trying to make a joke of it.
Not sort of. He wasn't happy with it. He was trying to show that there's a dilemma here. He was trying to show that there was a dilemma, but it also illustrates the mechanism, because the point is, if it's really the case that a particle on its own could theoretically go through one slit or another, until you know it's hit the other side, from the mathematical point of view, probabilistically, it's got to have some possible. This solid object sort of could, if you repeat it many, many times, could have gone through either. So therefore, until it's actually hit the other end, you've got to assume it's gone through either or. You don't know until you've measured it. And if you go back to the cat being dead or alive situation, it's exactly the same. It's both. Now the difference is that the mathematical structure, and now we use the word mathematics, unlike your sort of day-to-day solid sort of football example at the atomic level, is structured so that the dead and alive state have to be both there at the same time. The left and right slit both have to be part of the equations until you've measured it, because when you put it through that famous Schrodinger equation, you don't know where it's going to go. So the state it's got to go in at, it could be either. So you can't say it's gone through the left-hand slit. When you put it through the equation, it has to go through either. Until you've actually measured it, the wave function has to account for both possibilities. Yeah. So in this case, same case as a cat, until it's actually measured, you have to assume it could be either, and therefore you represent it mathematically as both. The question is it just a mathematical trick? Are we just saying we don't really know, so therefore it could be either, or both? Or could it really be both? Does it make sense? Obviously for a cat it makes no sense, it's both dead and alive. But could it actually be both? Could it be that the the electron has actually gone through both in some sense slits, and that state of affairs where all possibilities, in fact not just two possibilities, it could be many possibilities, can coexist at the same time, is called superposition, and it's that's the nature of quantum things. So at a very small scale, instead of saying that they're either spinning upwards or spinning downwards, or they're going through a left slit or right slit, or they could have this range of possible speeds, you just say it's got in a state of superposition, like a suspended state, where it can be all of those or any of those. Yeah, yeah, that's it. And until you go and measure it, and then snap, it will fall into one of those. So that looks like a mathematical trick. But the question is, when you look at the experiments, and I won't go again, I don't want to get into too much pure physics. It would be wrong to do that. You can do the same thing with polarized light. You can do electrons and their spin. You have to use a mechanism where you have to account for both possibilities. So that, in a sense, you could assume they're both, dead and alive, or spinning up and spinning down, until you measure it. Because if you were to know it beforehand, it would make no sense, because you can't know it beforehand. We've known that from the experiments. So we don't know it until you've measured it. So before you measure it, you have to assume it's both, somehow superposed on top of each other. You just don't know until you've measured. So that's called superposition. Such a big dilemma that, like for instance, we'll come on to that in a minute. To come into the state, I'll explain to you in a minute about why it's such a big dilemma. That I'll actually jump onto something to do with spin now. Again, I don't want to get too much physics here, but it's possible in this particular, the subatomic level, for that dilemma to exist in this way and be set up such that you have one state, one wave function, not two wave functions, one wave function describing a pair of particles. And the thing is, whereas you would like to know something about the first particle, and you'd like to know something about the second particle, like two electrons, in quantum theory, because it has a mathematical structure, and we use this dead alive phenomenon, it's possible to set up in practical experiments as well, the state whereby there's not one wave function, not two wave functions, just one wave function describing both. And that state is called a singlet state. In other words, the particles are behaving like one quantum object. And that is the heart of entanglement, the dead and alive together, right? But in this case, you've got two particles, but one is spinning up, one spinning down. And you can create a state whereby you know that when one is spinning up, and then you experimentally try to measure one of them, you find the other one's in exactly the opposite spin instantly, not like after a while. And if you try to guess, if you think, well, I'm going to guess which one's up and down, but you can't, because you're not allowed to know that. You know that from the theoretical structure. You can't know it. You cannot know it. You can't know the position, the momentum of the particle. You can't know that. You only know a range of possibilities. In this case, you can't know if this one particle is spinning up and its pair is spinning down. You know that they're in a state where one is up, one is down, but you're not allowed to know it until you measure it. So you can't know it. It's not that you're not allowed to, you cannot actually know it. So that's actually the heart of entanglement. Basically, this is the most mind-blowing phenomenon, because what it means is this, that according to classical physics, and I call relativity as well as classical mechanics, balls and Newtonian mechanics, all that classical physics, you should know everything throughout the whole time and work it all out. But in this particular case, you can't know it. The only way you can deal with it is after measurement. So here you have two particles that effectively could be almost at other ends of the galaxy, and when you measure one, the other one instantly appears in the other direction. Without any delay. I don't mean just instantly. The moment it appears. And before you measured it, it actually hasn't got an up and down position. Remember that. It can only have either or. But when you measured it, you snapped it.
So is this now we're talking about experimental level or theoretical level again?
Experimental.
Experimental.
Yeah, you measure it. Yeah, you actually measure it. If you measure a particle in that state, a pair of particles in that state, measure one of them, and you know that you can, in theory, in physics, you can create a pair of particles in that quantum state from the physics. You can actually do it experimentally. So this is what entanglement is. Before that, remember, you're not allowed to know anything about it, but you know one is up, one is down, but you don't know which one it is. As soon as you measure it, the one that you've measured is either going to be up or down. But as soon as you've done that, instantaneously the other one is up or down. Now here's a big problem. What if that particle's here? Okay, one's here, one's over there. It's fine. You could probably imagine that there's some sort of signal that's told this particle to say, look, I'm up now, you better go down. But what if it's like gazillions of light years away? No. If I said that you're going to drink tea and you're going to drink coffee, right? And you are a billion light years away, there's no way you're going to be able to tell your colleague that, you better have coffee, I'm having tea. It's not possible. There's no way for a signal to travel from one end of the universe to the other instantaneously, because what it does, it defies the most important fundamental rule of relativity, which is the fastest signal is the speed of light. It breaks the rule. And because it can't break the rule, because it can't really, because it's a rule. But how does it break the rule? The only way that Einstein could think was it's got to be, if you're going to measure one, it's going to be up and the other one's going to be down. There's some way that the signal has to have gone from one to the other. He says it can't be possible. It's impossible. So the only way to deal with that is they must have already known beforehand that one is up and one is down. There must be hidden information. Yeah, go ahead.
Is there a size limit to the particles?
Obviously, all of these things come on to size in a minute. Size is critical for all of these things. We're talking about a very basic experiment, but it illustrates the point that applies to much bigger particles and much bigger structures.
Speed of light.
Yeah, sorry.
Speed of light is what we've measured on the Earth, right? So maybe we haven't come to measure something beyond that yet. But it's technology.
Yeah, no. The thing is, this is already experimentally proven. It's not test. It's not a guess. You test. You set it up so that the particles are too far away for to signal to travel, and you can see that it's instantaneously changed, snapped in position instantaneously.
The assumption that's actually travelling from one part to the other.
Yeah, and that's the assumption. Yeah, and the thing is, that's the whole point about entanglement. They're not actually.
Going back to the assumption, I'm just saying that speed of light is what we've recorded, isn't it? It's the fastest thing.
Yeah.
But maybe we haven't got the technology to go beyond that yet to find something that's faster than that.
A very good question. A very good, statement. I like the idea, and that's the other possibility. But the problem is there's still a delay, and the problem is it's instantaneous. Yeah. So it has to be infinitely fast.
Yeah.
So therefore that's the dilemma. But the point is, that's probably not what's happening, and that's what you'll see. The point is, that's not actually what's happening. Those two things are like one, and that's what entanglement is. They're entangled, so that they're literally behaving as if they're one. So there's like you've got a twin, the other end of the universe is doing exactly what you're doing in reverse, the opposite to what you're doing. Or you think of it as doing the same as you're doing instantly, like a mirror image of yourself.
This becomes very, very interesting when we start to reflect about the universe.
Yeah.
And light traveling from stars.
Yeah.
So far away, so long ago.
Yeah.
But we can get into that.
Yeah.
So for a layman, like you're saying, these particles move up and down. So what sort of experiments have we done to say one behaves one way, one behaves the other?
This is in the realm of physics. It's not. Suffice it to say, it's very straightforward to set up an experiment where you entangle two particles like this. It's done all the time, every single day, and you can do it with many different objects. So you normally say you take something like a beam and a certain atom which releases two electrons in a certain state. So you can set it up.
Something more
Very-
crystal.
yeah, that's right. Yeah, that's right. There are items. So in other words, this is an experiment, not a theory. Again, going back to this just going back to like the double slit. This is an experiment, not a theory. So you do this and you see this happens. So this cannot be explained. Einstein was disturbed by because he was assuming that the only way that one could know what the other one is doing is because of some signal.
Spooky action.
Yes, exactly. He assumed that. And then there was a 1960s. There's a guy who actually solved the problem indirectly, called John Bell. Now, unfortunately, he didn't survive very long and didn't get his Nobel Prize, which he should have got. As he turned this dilemma, which Einstein and Bohr fought over. There's a picture of them fighting here, disagreeing, publishing articles against each other, and so forth, called the EPR paradox and so forth. Einstein came up with an elaborate paradox with Rosen and Podolsky. He basically was shattered by Bell. Bell was an Irish physicist who turned the whole debate into an experiment and actually a practical test. He actually, you see his books and his articles and things related to it. He talks about wearing two different socks. A simple experiment. He can show probabilistically what's the relationship between one and the other. And he came up with something called an inequality, like a mathematical inequality. If you repeat the experiment so many times from different angles and different positions and different spins, you see what the result should show is that the probability, if there is information already released between the two, that one already knows what the other's doing, that there's a way that you can work out. It's complicated, okay, but theoretically it doesn't require any quantum theory. It's just a probabilistic result that shows that if they are already have information about themselves, then if you repeat the experiment that many times, then the outcome will be this number, right? But if it's bigger than that or defies the inequality, then
So essentially, Bell is trying to prove, or the experiment that he was doing was trying to show whether those particles, when they were entangled, before they were measured, whether the information had already had the opposites before you'd even measured it.
Precisely.
Or the fact that when you did look at it, it then changed.
Yeah.
Which is why his experiment
Precisely. And you said it, and that's really it. So apart from the double slit, this is the other big thing. So yes, exactly right. So he came up with a way of testing whether it's either of those two. Perfectly put. So in a nutshell, this experiment has been this is actually an experimental test of the entangled states, and it's probably been tested maybe several thousand times. The most famous time is by a physicist called Aspect, like ASPCET. Now, without any failure, it's proved that before the particles head off, they are neither in one or the other state. No, they are beyond. There's no hidden information.
So Einstein was wrong.
So in other words, what we're saying is, okay, those are the others. This is a very rough, very bad picture, but it gives you an idea of reality. Reality is that in this case, spin, before they head off, they're both in neither up or down states. They're in a superposition of some sort of fuzzy state. One is the opposite to the other, and it's the reality that they are not in a fixed state. And this is the most powerful result you can ever imagine. It actually shows beyond doubt that what we think is a predetermined state is so undetermined, non-deterministic that it actually requires measurement even to establish spin is up or down. And here's a picture of fuzzy reality. Yeah. That's it. But, so in other words, at the atomic scale, subatomic scale, there is no such thing as a deterministic principle, no absolute value. So you've got a range of possibilities, that's all. Now, what does this all mean? Because you're going to say, I'll come on, one more comment. I should just say, this is very interesting. Erwin Schrodinger said that. It's clear from the measurements, that if you hear examples of momentum and position, that you haven't. This is what Schrodinger said in 1995. You haven't found a particle, for instance, at a position. You've actually produced one there. That's it. But before you've taken the measurements, it's just a big cloud of possibilities. And this is not just one physicist view. You'll find that a whole series of very famous physicists all held the same view, that somehow by actually measuring something, you've actually created the outcome by measuring it. Before that,
created the outcome.
yeah, being created. I don't. You care to use the word create.
Yeah.
You snapped it into a value by being aware of it. Yeah, you don't create anything because we're not creators, but we effectively, the particle has appeared because you measured it. It's in a position because you measured it. Before that, it's got a spin up or down because you measured it. Not before that. There's nothing. Now, this is the most powerful result because Bell's theorem, the defying of Bell's theorem, shows that experimentally that reality is in this state. It shows it, it proves it, and it's a very powerful result. And it just shows that, in fact, effectively, you're going back to your original double slit. There's a fuzzy reality. One electron is effectively, for all intents and purposes, has gone through both. You don't really know because before that state, it doesn't really exist as a particle. It's just a wave of some sort until you measure it and it snaps into one position. So it literally has no distinct measurement. Here's a diagram of like a smooth wave function. When you measure it, it snaps into one particular point. That's what you call collapse of the wave function. Okay? So now comes the big questions. Big question: how do you deal with this measurement problem, and how do you then interpret it? Because how can you deal with it? Because there's no mathematical way of dealing with it. Is there a way of getting around this? So there were two ways, and the most famous way is known as the Copenhagen Interpretation, right? I haven't put it on here. It's the most standard way of dealing with it in the whole of this world as we live today at this time moment. Currently, the mainstream of physicists, it's called, let's forget about it. And the other way of putting it is, let's shut up and calculate. That's it. That's the Copenhagen Interpretation. You can see that if you go back to Bohr here, forced to sum up that if in one sentence, if the Copenhagen Interpretation says to me, it will be shut up and calculate. That's it. And that is basically the way physicists today operate. So you will see...
Ignore it.
Yeah, ignore it. They said it doesn't matter. All we know is that this equation works. Nice little equation. We've got a range of possibilities. It's one of them. We could do all the calculations. It works for our day-to-day play. We're not going to worry about how it actually reaches value.
Basically means we don't understand.
Yeah, we don't understand. Yeah, we don't understand. And how can we get around this problem? There are several ways. Well, what we do understand is that we need to be aware of we need to be conscious. You can't just measure it with a lab machine. You have to go and measure it and physically see it. We know that because no one can tell you a cat's dead or alive until you open the box and look. Yeah. So that's the first and most important thing. Human consciousness or awareness becomes part of the theory, and it's the part that everyone's running from. Yeah. Like you see these scarpering physicists running away from scientists. Actually, not everyone, because some of them really understood that human consciousness was very important, like Wigner and all these people in Schrodinger. Lots of people did take it very seriously that there's human consciousness was the root of the collapse of this wave function, how something goes either left or right through the slits or goes up or down in the spin. And before that, it's just a fuzzy nothing. They realised something's happening. The human mind, the awareness, is snapping it into a state. But there are 2 or 3 ways out. It's actually only 2 ways out, right? Let's be honest. There are lots of strange ideas. Right. The one that you won't hear about so much is called spontaneous collapse, GRW, right? That's the one that's taken semi-seriously, and it relates back to your idea that things get bigger and bigger and bigger. Does it eventually collapse? They know that after things get bigger and bigger and bigger, you get more and more molecules and particles all connected together. Eventually, something gets big, and then it suddenly will collapse. Now, there's lots of studies on that. There's no results on that one at all. By the way, nobody has the answer. There's theoretically some experiments with buckyballs and large particles, but nothing has come out. So that's different from when you get to our level where other effects occur. You're not really seeing the quantum phenomenon at all. We're talking about large molecules. There are other things that are misunderstood. Physicists will come up to you and say decoherence, please ignore them, please, right? I'm not saying that because I'm a super physicist. It's just that I know the authorities in the field, and it's absolute bullshit, because the decoherence is a mechanism whereby the environmental influences can change the state of a system and cause it to interference, makes it lose its quantumness. That's not collapse, right? Because you get lots of different quantum states coming out of it. So that's not an answer. The only sensible answer, you'll hear Brian Cox talking about this, is that he puts it in the title of his book, that anything that can happen does happen, right? Yeah, that's the answer. It's just, let's talk more about fairies and pixies and things, right? Anything that can happen does happen because it's a fairy tale. Of course, well, in order to do that, this is what you need. So, a good friend here, Abu Bakr, would go get today to decide he's going to have tea. But if you put a cup of tea in front of him and a cup of coffee in front of him, what this theory actually says is that in one state he could go to either, right? But in order to get around the problem, let's just say he's doing both, but the entire universe splits into two universes. One here he's drinking tea, and one here he's drinking coffee.
The many worlds.
That's the many worlds, and that, as Brian Cox says, anything can happen will happen. Why? Well, because it's a mathematical quirk. Because of a generosity of someone called Wigner, who's a physicist, who a brilliant physicist who believed in consciousness being collapsed, he let this guy called Everett onto the podium and give us present a paper which he thought was okay, which gave this solution. Not to be taken seriously, but because the math shows that maybe if that happens, you can get round the problem, because all you do is just pick the one that you're seeing. Yeah. So if I go from here, you're going from here to the restaurant over there. You could have gone that way. You could have gone that way. You could have gone to the bathroom first. Now, in each universe, there's one of you doing everything. I mean, this is the problem, because of course, how can you ever test that? Now, let me tell you something else. The first thing is that physicists will ignore collapse. Second thing is they will believe in this fairy tale over anything else. And it will require so many universes to exist simultaneously that anyone would not take it seriously. So the most famous physicists, like Feinberg, who was a Nobel Prize physicist, it's just too much. What did he use as basically fanciful baggage? Fairy tale baggage. It's just cannot be the case because it's no longer science. You can't test it. There's no way of testing it, and there are even philosophers of physics who will believe that as your first choice. Yeah. So there's another view as well that I haven't put on here, which another way of looking at the wave function, which is slightly different, tries to get around it. But again, there's no solution. So the only solution we have left is still that human awareness and human consciousness is doing something.
So here, what I want to do is, I want us to potentially look into what are the theological or philosophical implications of what we find here, right? So in an atheistic worldview, obviously this shatters that.
Yeah.
Because you're saying things are, as you alluded to earlier, if you take a reductionist type of approach to how reality is, then and I guess it falls into materialism also, in terms of just that the material realities are so separate, individual, no connection between each other, and it's random, blah 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 blah. If human beings are part of the equation of reality, then we know from a religious perspective that Allah Ta'ala has created the heaven and the earth for man. That هُوَ الَّذِي خَلَقَ لَكُمْ مَا فِي الْأَرْضِ جَمِيعًا. He has created for you all that's in the heaven and the earth. So man is at the center of man or min or jinn, or for both of us to and this kind of ties into that, I guess. If mental state of consciousness is a part of, I mean, I guess we want to, I don't know, you alluded to your view as well about whether we are, whether we are bringing into reality something, or whether we are determining reality to be in a certain way. So I guess that opens up a whole array of, I guess, a return back to theistic.
Precisely, and the point is that going back to right at the beginning, we believe that there's an ultimate supreme creator, and that we're here for a purpose. And this essentially says that nothing's the way it is unless we were here. There's no reality without us.
There's no reality without.
There's nothing.
Because we make it conscious of it.
We're making it happen.
This is the table.
Yeah. So much so that we are closely created by Allah subhanahu wa ta'ala for the purpose of this existence. That is, our existence around us is responding to us. It's tailor-made.
Tailor-made.
Yeah.
The cat in the box is only alive because you're looking at it.
Yeah, exactly. Nothing is actually here without a purpose, and we are very fundamental. We don't understand what that is, but this sort of should shatter everything like evolutionary ideas and things, because that cannot explain this at all.
Yeah.
There's no such thing as, it doesn't matter if we evolved or we were dropped here from the sky, or or some atom was. It basically doesn't matter, because at the end of the day, nothing exists without us being here in the first place. Yeah. Doesn't matter how we got here.
There's also, I mean, we didn't speak about this, and we don't need to go into detail. But
Yeah.
I know that when I was reading up on the delayed choice eraser kind of experiment, which we don't need to go into, but it also one of the things that come out to me was how predestination, things it's all within the qadr of Allah Ta'ala. Allah Ta'ala knows. I guess also from the quantum entanglement. I mean, we spoke about this before. And this is is an assumption that two entangled particles, which could be millions of miles away, are communicating with each other faster than the speed of light. But this is because they're even thinking that because they have an assumption that if there's not a creator, that the communication has to come from one particle to the other. But whereas we know there is no particle. There is nothing in this universe except that it's in Allah's control.
Yes.
So things don't need. So there's many things that come out.
Yes. Beautiful. And what I wanted to add to that, to be honest with you, is a solution on here which I haven't put on here, and I should have put on here actually, and it is a good solution. It's called superdeterminism, which basically means like lahu mafuz. Basically, from the physicist's point of view, that every single thing that's happened is determined, has already been predetermined and written in this qadr. Every single event is already there, written. That's superdeterminism, and that's the solution also to this problem.
This is what came out of John Bell, the Bell's.
Yeah, it's one of the
So
solutions.
explain that a bit. How does explain that again?
No, it doesn't come. Correction. It doesn't come out of John Bell. This is a solution to the whole problem of collapsing wave functions and the probabilities
Right, okay,
and
so
superposition.
It's already all decreed.
Everything is decreed. That's superdetermination.
The answer is clearly, because like this one's spinning here, and you look at it, that one's spinning the other. It would have had to have already have happened.
Yeah, that's one way of thinking of it, and it works as a massive, gigantic solution to the whole problem. And it's really essentially saying that it's called superdeterminism. It's not a theological word. It's not a philosophical word.
Yeah.
It's physics. It's called superdeterminism, and it's just basically every single thing has been predetermined.
Is this what they mean by the future has already predetermined the past?
Yeah, literally everything determined is written, and that's one way of looking at it.
You know, I mentioned earlier about light traveling from stars, which could be 1 million miles away,
Yeah.
1 million light years away, for
Yeah.
example. Now that light, you know, obviously, when it comes to us, is it a particle or is it a wave? And obviously, like, because that light has already left its source 1 million years ago, or 1 million light, or how many years ago, and that light has been traveling through the universe. But when it hits us, if we then, if we then try to measure that light, obviously that light had already begun its journey so long ago. Have there been any experiments to kind of see if you know, by us affecting that measure or measuring that light, does it then behave as a wave or a particle, and what does that mean in terms of that journey having begun so long ago?
And the rules are the same. It's no difference, because basically we know that it's not either a particle or wave. It has a wave equation.
But when it was traveling through the Earth, traveling through the universe, before you even looked or tried to measure it, was it a wave or a particle?
It's both, because the whole thing is that these things, neither one or the other. It's this object from a quantum point of view. It's a superposition. It's both behaving both ways.
So but when we measure it, it acts like a particle.
Yeah, well, it depends on if you see its behaviour. It depends on the context. What you're referring to is what they call classical picture of general relativity. The classical picture works because at the scales we're looking at and the sizes and distances, its particle behaviour is not relevant. It's not doing any interaction with anything. We just
one or the other.
but when you actually look at it close up, and behaviour, it's both. Yeah, it's both until it's measured, and its behaviour is a combination of both. You'd only notice that if you're seeing it interacting with other particles. When you do physics, equations, you use the equation, or like a wave equation for each one. In fact, all of these physics requires it to be something, like both. Its behaviour is no different. It's just that on a very large cosmological scale, it works very, very well just to think of it as a sort of a beam or wave. You don't need to look at the quantum side because you don't need it. It's too big, too far.
Is there anything else you want to include from the presentation, and then we can just maybe we can wrap up and ask any questions?
Yeah, I will do. Just about that. I was about to say one more thing. You mentioned. I will just drop a couple of hints here. You mentioned something about travel for a very, very long distance. I just want to say something not to do with quantum theory, but when light travels, it travels like with everything. This is general relativity on what's called a geodesic, which is, in other words, the shortest distance path. So we know that particles that travel very close to the speed of light from the early part of the Big Bang will have which are travelling close to the speed of light, have actually journeyed in real terms just for a few seconds or days, even though the event happened billions of years ago. So if you, in other words, put a real clock on a small particle that's travelling close to the bird, it's just travelled for a couple of days. Some of the beams you see have only lived for a couple of days, from the origin of the Big Bang, because of the nature of time. So, in other words, the time's it. So I'll tell you where I got this from. This is a fact. A, it's a fact. It is a fact. B, the most. I have a superb lecturer, professor of physics, called Faye Doka, who was Stephen Hawking's PhD student, and she is a professor at Imperial. And one of the lectures she gives at every single lecture shows she refers to the light leaving on a Tuesday and arriving on particle leaving on Tuesday, arriving on Thursday. In other words, there's a sort of like a coffee time conversation she had, because if you look at a particle that was released at the point of the Big Bang, that's speed is very close to the speed of light, right, from the beginning to now. Its trajectory in time is what we call a proper time. If you could strap a clock to it, it's just been a couple of days, even though it started from the billions of years ago.
For that beam of light.
Yeah, for that particle. Yeah, because time doesn't. Yeah, that's it. So time is complete illusion, by the way. Yeah.
Are you really here? No.
Yeah,
No, sorry. Can you try to explain that one more time?
Yeah, I'll explain one more time. In other words, because particles from the early speed affects the movement of its own time scale.
Right.
If I was shooting you through the universe right now, at close to the speed of light, right, we'd all be like probably gone. But suppose you went for a half a second, and we'd be like ready for retirement or whatever.
Sorry.
Yeah.
The closer you move to the speed of light, the slower time.
Yeah. Your clock would just switch right or turn right down, so you just slow down.
Okay.
So particles that are running very, very close to the speed of light have actually literally only taken sometimes days to arrive actually here.
But the question, when you say, that star there is a million light years away.
Yeah.
Okay. Are we still applying that to that as well? So the actual light that's come from that star.
No, I'm not talking about that.
Yeah.
I'm actually talking about particles, not light.
Yeah.
There was something that has mass, because photons, which are light, don't have mass. Something that can't travel the speed of light, but is very, very close to. So that if you strap a little clock to it from the beginning of the Big Bang till now, if it's closing very, very close to the speed of light, its proper time, in other words, time it's recorded on its own clock, the same clock you and I use now, or whichever watch you like, is just a few days.
It happened billions of years.
Yes. So
but
don't be
the
deluded.
speed is traveling. That clock is going by the Earth clock, aren't we?
Sorry?
That time is the Earth's time. The clock that we would use to look at would be at 24 hours, right?
Yeah. So whatever because remember, there's no such thing as Earth time. It's just time is very much dependent on you. It's another very observer-dependent thing. Time is, and just one more word on that is that if you're traveling much faster than I am, or I'm, significantly faster, everything that seems to have happened simultaneously to you, like you set off 2 fireworks at the same time, right? You go off speeding really, really fast. I mean, very, very fast, and say, I've got these 2 fireworks. They go bang, right? Bang. For me, one would occur before the other. Go bang, bang. I'd see them at 2 different times, and because what's simultaneous for you is no longer simultaneous for me.
Mm-hmm.
That's a fundamental fact. So in other words, I know things, and I can see things. You can see things that would be in my future, technically, and I can record some of your past. Time is an illusion. It's a very strange thing. I won't talk about this too much. I just drop those 2 things. But that's another thing. It's just failure of simultaneity of time, and the fact that yes. Before we finish, I'll just do you one last thing, because we'll do it another time. But I want to show you this, that in relation to human consciousness, the big chapter will be the whole series of basic theories and ideas about how to quantify human consciousness. And I will just add to you something to take home, is that whereas we try to incorporate something to do with collapse theories. I can't see it on here. There's no diagram. Sorry, but basically, collapse theories are sometimes used as something happening inside the brain at specific physiological points. And one of the most famous ones is Roger Penrose and Stuart Hameroff, who both of whom I've spoken to and know, and they worked on the theory for like 20 plus years about what's called objective reduction, whereas collapse occurring in some structure of the brain. It's just an idea. So just to show you that these ideas about consciousness and collapse are taken very, very seriously, so they're not just fanciful ideas; they're experimental evidence. So there's work being done on them. Human beings' subconsciousness is very, very fundamental. And I just one more thing is that there's an aspect of human consciousness that is the way that we integrate information, that is separate, unlike an ordinary object like a computer, where you can compartmentalize different files. If I see you sitting in here, everything is integrated. Everything's together and in relation to each other. There's a whole theory called integrated information theory, which is working very, very much on that. Again, trying to find if there's a way of quantifying human consciousness. All of this so that we can get to the bottom of the idea of the collapse of the wave function and more. There's a huge amount, and these are proper bona fide physicists working on this, as well as biologists and neuroscientists, lots and lots of people. Anyway, there's a lot more to say. I'll just say that to you. So in other words, it's a huge, what I've told you is just the alpha, and we're going to go so gamma and whatever. We've got to go to a whole lot. There's a whole lot of information to convey to you, but the take-home message would be: don't be fooled into believing that we know how the universe really, really works. We're still working and grappling with it, but we do know that there is a fundamental problem in the science that it cannot do without human awareness somehow, and that we are definitely not some random byproduct of random processes, and we are here for a purpose. And I think I would say that here's a really nice little quote. I'll just end on this. It's a very nice quote by Paul Davies, and he's a physicist too. He also set up the Institute of Astrobiology in Australia. He's a physicist here. He spent years grappling with the idea of purpose and meaning, by the way. And he finally concluded with this beautiful article. He says that, what does it all mean? What is man that we might be party to such a privilege of being aware of everything around us? I cannot believe that our existence in this universe is a mere quirk of fate, an accident of history, or an incidental blip in a great cosmic drama. Our involvement is too intimate. The physical species, Homo, may count for nothing special because we look like a blob of biological tissue, but the existence of mind in any organism, being a human being, on some planet in the universe is surely a fact of fundamental significance. And through conscious beings, the universe has generated self-awareness. It can be no trivial detail, and no minor byproduct of mindless, purposeless forces. We are truly meant to be here. Yeah.
Meant to be.
Yeah, we're meant to be. We're placed here. We've been created by Allah, subhanahu wa ta'ala.
So, alhamdulillah for that. I think this has been, I think, one of the catalysts that may have caused a paradigm shift definitely in a certain quarter of the Western academia, away from atheism towards believing in they may not making that jump straight away, but certainly there's a whole, the direction has changed, I believe, especially in certain quarters of within the sciences and learning and whatnot. So thank you, Jazakallah khair, for coming and sharing your views. Is there any other thing that anybody else wants to ask? At this stage. One more last question.
Can I quote Surah Al-Mulk, the line, Bismillah ar-Rahman ar-Rahim, قُلْ هُوَ الَّذِي أَنْشَأَكُمْ وَجَعَلَ لَكُمُ السَّمْعَ وَالْأَبْصَارَ وَالْأَفْئِدَةَ قَلِيلًا مَا تَشْكُرُونَ. In other words, it is He who Allah has brought you into being and gifted you with the power of hearing and sight and faculties. He's endowed you with a seat of feeling, understanding, thought, consciousness, intellect and volition. How little you render thanks to Him in return for the benefits and His favours.
I think throughout the creation, you do see this relationship between the creations. So I think it's more vividly present or demonstrable. Demonstrated in, for example, the relationship between certain bees and birds and certain flowers, and you can, it's completely obvious that one thing has been created for the other, or for the purpose of the other, and that is also within a system of, you know, within this whole ecosystem of different creatures, you know, living and showing that, you know, the relationship between them. And I think with insan, you know, for insan, it's like what I began the ayat in the beginning, that inna fi khalqi samawati wal ard wa ikhtilafi al-layli wal nahari la ayat li ulil albab. That in the creation of the galaxies and the heavens and the earth and the alternation of the night and the day, there are signs for the people of understanding. الذين يذكرون الله قياما وقعودا وعلى جنوبهم. These people of understanding are those who remember Allah sitting, standing, and lying down. And they are complementing their dhikr, the remembrance of Allah, with what? وَيَتَفَكَّرُونَ فِي خَلْقِ السَّمَاوَاتِ وَالْأَرْضِ. And they are reflecting upon the creation of the heaven and the earth. So there's this. What does this teach us? It teaches us that Allah has created and left signs for human beings in what we see in and around us, and those signs, from the grand macro scale to the micro scale, they just demonstrate so many. And those signs they have so many different implications. They have so many different implications, and then they conclude, "Rabbana ma khalaqta hadha batila." That, oh Allah, oh our Lord, you have not created this for no reason. We see purpose. And it seems like, from the implications from quantum mechanics is that we're not only just casual observers, but we're kind of intrinsically involved in this kind of you know, this we're not just a part of observing reality. It could be much more than
active participants.
Active participant.
Yeah.
In that, and which is, and I guess this I want to end with this, and this is what's amazing, that the creation of Allah Ta'ala, whether it's the study of the cell. I remember talking to a PhD doctor who had been studying diabetes and studying the relationships of the communication between the cell wall and the nucleus, and the various routes that are taken, and how there's just so many, and then it would take, you know, so many thousands of years for us to be able to kind of track all those communication routes, and it's just so much to study. That all these demonstrate to us that we are not even touching the surface with regards to the depth of information that exists behind this creation, and no human being would ever even come close to living that long enough. So the purpose. So then the question is, why is there so much depth, and why is the science so innumerable, when no human being, even if in a combined capacity could we ever reach conclusion in terms of lessons, in terms of understanding? And that is because we're in this world as a taster for the afterlife, so that when we enter the afterlife and we make it back to Allah the Creator, we just have eternity to continue that journey of discovery and learning, so that what we only but felt and seen here was a taster of what's to come. So like in the ayah of the Quran, that when they have the pomegranate and they say, oh, but this pomegranate is just like what we tasted in the world, there's a similarity. So in Jannah, a person who is in awe of Allah, who is in trying to learn and glorify Allah Ta'ala, will just spend eternity doing so. So I think it's just transition and the trajectory towards eternity. That's a journey that a person is on a path of discovery, and this just kickstarts it.
Beautifully put. Love it. Thank you so much. It's fantastic. I did notice that when you did say one point in there that it is those who reflect as well. I just want to point out that this is very important that we all do encourage reflection on science as well as everything else. And you mentioned the orbits of the planets and so forth, and those who reflect and think. And this is what's a trend that we want to try to reverse, and Muslims being shying away from that, because we should be at the forefront of science, not the back of it. So we should be the cutting edge, right? So no shying away from it. And this is a wonderful opportunity to maybe inshallah build on this and project this passion to everybody, inshallah.
Inshallah.
Yes.
Jazakallah khair. Jazakallah khair. Subhanakallah wa bihamdika ashhadu an la ilaha illa anta astaghfiruka wa atubu ilayk.
أشهد أن